All right, folks, we are back. We're looking at section 7.5. If you are taking this course in January of 2022, then this will not be on the any assessments through this course, but otherwise it very well might be. Now here we're looking at solving linear trigonometric equations. This is a skill that will absolutely be called upon in calculus when you get into that course, so we need to be ready to handle it. Now, let's take a look at the graph of y equals the sine of x. You might say, hey, Mr. Pasotka, there's no graph right here, and that's because we haven't drawn it yet, right? Sketching the graph of y equals the sine of x, we should be complete masters of it by now. We've done it over and over and over again. We should be able to recognize the shape. We should know where its maximums and minimums are, and we should be really, really comfortable with it. If we're sketching it through its anchor points, then we have 3 anchor points along the horizontal axis. And we have a maximum and a minimum, and our general shape looks something like this. Nice, smooth, and it gets a little bit steeper than we want. That's okay, we're doing our best, and I'm just going to freehand that a little bit here. We're looking at a shape generally like this. We have arrows on either ends to show that the pattern continues in both directions. Now, if we're taking a look at this graph, and we're asking ourselves, okay, when or where does the sine of x equal 1 over 2? Well, I know my maximum values here are at y equals 1, right? Okay, so if there's my maximum value, about halfway, that's going to be where the sine of x equals 1 over 2. I could use my related acute angles to find all of these values right here, but the point that I want to make here is that our function, the sine of x, is equal to 1 over 2 an infinite number of times, in an infinite number of locations. That doesn't mean it's equal to 1 over 2 everywhere, but it does mean that it's equal to 1 over 2 a certain number of times over each period. In this case, if I take a look just at one period here of my sinusoidal curve, then I can see my function equals 1 over 2 at two different locations along each period, right? And along the next period, again, it's going to equal 1 over 2 different times. All right, so where we're going to look right in here is we're going to solve these linear trigonometric equations, meaning we're going to be given equations like this, and we need to find the solution. We need to find the x values that make the statement true, that make this equation true. So if we're solving a trigonometric equation, then it's actually going to be pretty darn similar to how we've solved linear or quadratic equations in the past. All right, so first off, we'll isolate for, in the past you isolated for your variable. This time we're isolating for the trig function itself using our inverse operations. You've done that before. You've been doing that all course. You've been doing that since grade 9 and even before. Next, we'll find the related acute angle. You've been doing that since chapter 6. You know how to find a related acute angle. Then we'll use our related acute angle with our cast rule. Again, we've been using this since chapter 6 to find the solutions for one period. And then we're going to find other solutions within a given domain. Each of these problems that we'll be working with will give us a certain domain to work with. And if not, then we need to start writing them in a pattern, but that's okay. We're not going to get there yet in this lesson. Now, we'll look at our first example. We'll solve our first trigonometric equation, and you've actually solved problems like this already in the course, but we want to go through it through the lens here so that we can work to complicate it with future problems. All right, so here we're working with the sine of theta equals negative root 3 over 2. Our very first step, we need to isolate for our trigonometric function using our inverse operations. So where's our trig function here? Well, that's the sine of theta. So if we're trying to isolate it, that means we need the sine of theta to be all alone on its side of the equal sign. Well, hang on, already that's done for us. All right, so this very first problem, we don't even need to isolate. They did that for us. Well done, lesson makers. All right, now we need to find the related acute angle. We know how to find a related acute angle like this. If we're finding a related acute angle, then we know we're working with the sine of theta. The sine of theta is opposite over hypotenuse. Right? If we're working with a related acute angle, that means we're sort of working in quadrant 1. And if we're working in quadrant 1, then really we only need to consider the positive version of this value. So in quadrant 1, because it's our related acute angle, we need to sketch our special triangle. So we're going to ask ourselves, okay, which special triangle has an opposite side of the square root of 3 and a hypotenuse 2. So that means 2 is on my hypotenuse. Square root of 3 needs to be somewhere in here. Luckily, we've sketched this special triangle so many times that we could sketch it in our sleep with our eyes closed. And that brings us to pi over 6 up here, pi over 3 down here. And we ask ourselves, okay, which angle has the opposite side as the square root of 3 and the hypotenuse of 2? Well, that's going to be that's going to be pi over 3. All right, so the pi over 3, what we're doing here is we're finding our related acute angle. Our related acute angle is pi over 3. All right, fantastic. Now that we've found our related acute angle, well done us, then we can use our related acute angle and the cast rule to find the solutions for one period. The cast rule, okay, well, if I'm looking over here, back into my equation, I've realized that my sine ratio, it's negative. So I need to ask myself, okay, in which quadrants is my sine ratio negative? Well, sine, according to my cast rule, sine is going to be positive in quadrant 1, positive in quadrant 2, negative in quadrants 3 and quadrants 4. So we're looking specifically at quadrants 3 and 4 right here. Right? So if the sine of theta is equal to the square root of 3 over 2, well, that's going to give me two solutions. It's going to give me one solution in quadrant 3, and one solution in quadrant 4. All right, so here we're working, and we can say, okay, our angle in quadrant 3, we'll call it theta 1, is going to be, because it's in quadrant 3, it's going to be pi plus my related acute angle. And if it's pi plus my related acute angle, I know my related acute angle is pi over 3, so that means I'm working with, and I just crashed, bear with me, you get a nice shot of my desktop there. We're working with pi plus pi over 3. Nice and easy. We can do that in our sleep. We're working with 4 pi over 3. That is my first solution. All right, and then I can take a look also at quadrant 4. All right, in quadrant 4, we'll call this one theta 2. Then we're working with 2 pi minus alpha. 2 pi minus alpha, that's 2 pi minus pi over 3, and I'm working with 5 pi over 3. So these are my two solutions within this one period. All right, we're done that. Well done us. Now we need to use the period that we've worked with to find any other solutions on the given domain. In this particular case, and we'll go over an example afterwards where we go a little bit deeper. In this particular case, our given domain is in between 0 and 2 pi. So we've found all of our solutions, because between 0 and 2 pi, we've found those two angles here and here. And if we kept on going, then we're no longer within our given domain. All right, so the two solutions, we can give a therefore statement. Therefore, theta equals 4 pi over 3 or 5 pi over 3. All right, well, let's work a little bit further, and we'll work using these same steps along a more complicated problem. So let's try it out here. You'll notice I have copied our steps from up above. You won't have that, but you will have your pages right in front of you. So we need to isolate for our trig function using inverse operations here. And here we'll use a slightly different color for the very first step. We'll work with a nice magenta color. We're isolating for a trig function using inverse operations. Okay, so right here, our equation, and you'll notice the restrictions listed right beside that, so we need to be careful. Part of that's a restriction, part of it is our equation. With our equation here, we notice that we have trig functions included, but they're not isolated yet, so we need to isolate them. Now, if you're confused, if this part looks confusing to you, you can consider your trig function, it's just like another variable. Okay, we could consider the cosine of theta, we could replace that with x in every single place and solve it from there, but we're not going to, because we should be able to handle it a little more in depth by now. Okay, so we have 5 cosine thetas over here, we have 1 cosine theta over there. So that means we're working with 5 cosine thetas minus 1 cosine theta. And on the right-hand side, I'm working with -4. And I can add 1 to both sides, plus 1 over here. They'll cancel out on the left-hand side. I'm working with 4 cosine thetas equals -3. All right, so 4 cosine thetas equals -3, and this should be nice and straightforward. That means the cosine of theta is equal to -3 over 4. Here, I have isolated for my trig function using inverse operations. Great job, us. We have already completed the first step. You've already earned some marks here. Okay, now we need to find our related acute angle. All right, well, if we're finding our related acute angle, that means, so related acute angle in this case, it's a bit of a different process, right? So if our related acute angle, if our cosine of theta is equal to negative 3 pi over 4, that means the cosine of our related acute angle will be equal to 3 over 4. Okay, so if we're working with 3 over 4 here, we'll ask ourselves, okay, this is cosine. Cosine is adjacent over hypotenuse. If cosine is adjacent over hypotenuse, all I'm doing is I'm looking for one of my special triangles that has an adjacent side of 3 and a hypotenuse of 4. Oh no, well, we don't have a special triangle with an adjacent side of 3 and a hypotenuse of 4. So then we need to, for a question like this, and you will see them in the practice, but you will not see them if you're in my class, you probably won't see them on a summative, you need your calculator. Okay, so we're going back to our grade 9 skills. The cosine of a related acute angle is 3 over 4. That means I can take the inverse cosine of each side. The inverse cosine of the cosine of alpha is equal to the inverse cosine of 3 over 4. And if that's true, then alpha, because those cosines cancel out, the alpha is equal to the inverse cosine of 3 over 4. We plug that into our calculators and we find that alpha is approximately equal to 0.72. Okay, what is that in? Well, it's in radians, right? So if our alpha for related acute angle is about 0.72, then we'll head back up here. Whoops, and you know what? I'm lagging out. There we go, that's a little bit better. Our related acute angle, we found. Now we need to use our related acute angle and our cast rule in order to find the solutions for one period. Okay, so our related acute angle is about 0.72. Our cast rule tells us this trig ratio is negative, this trig ratio is cosine. I know the cosine is positive in quadrant, according to my cast rule, it's positive in quadrants 4 and 1, meaning it's negative in quadrants 2 and 3. If cosine is negative in quadrants 2 and 3, that's where I'm working here. And so I can use my cast rule, I can use my related acute angle. Here's where it's a little bit, it doesn't get too complicated yet. That'll be next example. Here we're in quadrant 2, so that means theta 1 is equal to pi minus my related acute angle. Well, that's pi minus 0.72 approximately, and that's into my calculator. I'm working with about 2.42. Okay, well, theta 2 is equal to pi plus my related acute angle, because theta 2 is in quadrant 3, and in quadrant 3, that's how we find our theta. So if theta 2 is equal to pi plus related acute angle, that is pi plus 2.42. That's approximate now. And that is approximately, pi plus 0.72. Sorry about that, folks. Meaning we're working with approximately 3.86. Okay, that's great. Now I've found my thetas, and then I can use my period to find other solutions within my domain. Well, the period here that I'm working with, because it's still a cosine function, and because the only thing inside my cosine function is theta, and that's a little bit of a hint towards the next problem, then my period is 2 pi. If my period is 2 pi and that's the domain I'm looking in, just like before, those are my only solutions. So therefore, theta is approximately equal to 2.42 or 3.86. Okay, well done. Now let's complicate it a little bit further. All right, so here, I have a new problem. This time I have a 2 theta inside my cosine function, inside my trig function. So we're going to work with this, and we'll see what happens. Okay, start us off. We need to make sure that our trig function is isolated. I see my cosine on the left side. The only other things I see on the left side are all inside the trig function. I can't get them out yet, so this is isolated, right? The only thing on the left-hand side is the cosine function. Okay, that's great. Well done, us. We're all finished that. Now we need to find our related acute angle. Well, our related acute angle, just like before, I know this says the 2 times theta inside my trig function. We're going to ignore that right now. Okay, so my alpha, and that is the related acute angle that will bring my function equal to negative 1 over 2, or really my related acute angle that will bring my function equal to 1 over 2. Oops, the cosine of alpha is equal to 1 over 2. Okay, well, I know how to handle something like this. Try it out on your own. Come back in 5 seconds to check out your answer. 5, 4, 3, 2, 1. Here we are. where our cosine of alpha, that brings us into our special triangle. Our special triangle tells us that the angle pi over 3 has an adjacent side of 1, a hypotenuse of 2. That's what we're looking for. So if our alpha is equal to pi over 3, okay, we can use that. Great job, us. We found, oops, where our procedure right here. There we are. Now we need to use this related acute angle and our cast rule in order to find the solutions for one period. Well, according to our cast rule, here we're working with the cosine. Our ratio is negative once more. So cosine, I know just like before, is negative in quadrants 2 and 3. Well, in quadrants 2 and 3, then my theta, well, really, in quadrants 2 and 3, then my angle that I'm working with is equal to pi. In quadrant 2, it's equal to pi minus my related acute angle. Now, question is, what angle are we working with? It used to be theta. It's no longer theta because this time inside my trig function, I have a 2 theta. So that is 2 times theta 1 is equal to pi minus alpha. Okay, great. If 2 times theta 1 is equal to pi minus alpha, that's nice and easy. I know my alpha is equal to pi over 3. Okay, well, pi minus pi over 3, that's 2 pi over 3. And then I can divide, if I'm isolating for my theta 1, that's the trick here. I'm isolating for my theta 1, I can divide both sides by 2, and I'm working with theta 1 is equal to pi over 3. Okay, great job, us. Let's try again here in quadrant 3. Okay, in quadrant 3, 2 times theta 2, still 2 times because that's inside my trig function. 2 times theta 2 is equal to pi plus alpha. Okay, well, pi plus alpha, that's nice and easy. That's pi plus pi over 3. Well, that's 4 pi over 3. What's equal to that? Well, still 2 times the theta 2. Okay, again, I'm isolating for theta 2. I can divide both sides by 2. I'm working with theta 2 is equal to 2 pi over 3. Well done, us. Now here, my domain, and yours will look a little clean in the mind, my domain is still 2 pi, between 0 and 2 pi. Well, that's great, but my period is no longer 2 pi. My period is now pi because I have a k value inside this trig function. This k value is equal to 2. My period is equal to 2 pi divided by k, and that is 2 pi divided by 2, and that is pi. Okay, well, if my period is pi, that means that I'm going to have each of these solutions every single period, right? So this is like a cosine function, the cosine of 2 theta. If my base cosine function looks like this, well, my this cosine function with this transformation is going to look something like this. And it's going to have 2 periods happening between 0 and 2 pi. Okay, that's great. That means that I'm expecting 1 solution, 2 solutions, 3 solutions, 4 solutions. Okay, so I'm finding 4 solutions. That means I just need to add a period to each of my angle thetas here, to each of my solutions here. All right, so that means that I can have a theta 3, which equals pi, and that's my period, plus pi over 3. And that is 4 pi over 3. All right, my theta 4, sorry, I know I'm getting messier and messier. My theta 4 is equal to pi plus theta 2. Well, theta 2, that's pi plus 2 pi over 3. And I'm working with 5 pi over 3. And there I have all of my solutions. Therefore, theta, whoops, how did that happen there? Therefore, theta is equal to pi over 3, 2 pi over 3, 4 pi over 3, or 5 pi over 3. Okay, well done, folks. If you were able to follow that, that's great. If you were not, that's okay. We'll get there. All right, looking then at example 4. Now, this one might look a little bit tricky. It might look a little bit complicated. But the trick is, just like before, we need to isolate for our trig functions. Well, we know how to isolate for trig functions. Well, rather, we know how to isolate for things. In this case, the thing we're isolating for, it's our trig function. So we can handle that. We know how to handle that. We're working here, and we have the cosine, everything in the middle. We don't really care what it is at this stage of the game. All we care about is that we're isolating for everything inside this cosine function and everything inside. So this is like we're working with 2 minus 2x equals 1. If it was something like this, we would easily know how to isolate for x, and that is we subtract 2 from either side. So we're working with 1 minus 2 on the right-hand side, negative 2x here, and that is negative 1 is equal to negative 2x, and that is x is equal to negative 1 divided by negative 2, and that's 1 over 2. Okay, well, let's isolate for our cosine function here. We follow the exact same steps. Where we see this 1 over here, we see this 2 over here, we can subtract 2 from either side. We're working with negative 2 times the cosine of 2 times theta minus pi over 8 is equal to 1 minus 2. Okay, well, 1 minus 2, that's equal to negative 1. Now, here I'm working with negative 2 times the cosine of da 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 da. I don't care what's inside. That's okay. All I'm doing is I'm dividing both sides by negative 2. And I'm working with the cosine of 2 times theta minus pi over 8 is equal to negative 1 over negative 2. That is 1 over 2. So you can see right here, I've come to this exact same conclusion. It just, when I substituted in x for my cosine function, it doesn't matter if you can't follow this. That's great if you can. It might help you clarify what we're doing here. Okay, that's great. Now we need to push right on forward. Okay, so if our cosine function, remember, our cosine function is equal to 1 over 2. Well, that means that the cosine of my related acute angle is equal to the positive version of that, and that's still 1 over 2. Well, the cosine of my related acute angle, if that equals 1 over 2, that tells me that my related acute angle is equal to, drum roll please, you can pause the video here as you work through it yourself. And I'm hoping you said, I think actually this is the same one as the last time, wasn't it? We're working with 1 over 3, sorry, pi over 3. Okay, so if my related acute angle is pi over 3 here, I need to set everything that's inside my cosine function equal to that, or equal to, rather, that after I put it into my cast rule. So we'll put it into my cast rule. If alpha is equal to pi over 3, if my cosine function, or cosine ratio is positive, then I'm working within quadrants 4 and 1. Okay, if I'm working in quadrants 4 and 1, then theta 1, or rather than the first theta that I'm working with, will equal pi over 3. But how am I working with that theta? Well, I'm taking the entire piece from the inside. So that is 2 times theta 1 minus pi over 8. All right, now I need to isolate for my theta 1. So I can divide both sides by 2. So pi over 6 over here. I'm working with theta 1 minus pi over 8. And that is theta 1 is equal to pi over 6 plus pi over 8. Oh, well, pi over 6 plus pi over 8, no, that's not easy, and that's okay. We're working with, we can multiply both the numerator and denominator by 4 here, so 4 pi over 24. Multiply the numerator and denominator by 3 over here, so 3 pi over 24, and that is 7 pi over 24. Okay, well, that's theta 1. Theta 2 is in quadrant 4. So theta 2, that is 2 times theta 2 minus pi over 8. Is equal to 2 pi minus alpha. And that's because that's how you find a terminal arm if you're working in quadrant 4. Okay, so 2 pi minus alpha, well, that is 2 pi minus pi over 3. Well, that is 5 pi over 3. And what's that equal to? Well, it's equal to 2 times theta 2 minus pi over 8. So I can divide both sides by 2, and I'm working with theta 2 minus pi over 8. Is equal to 5 pi over 6. Okay, well, if that equals 5 pi over 6, then that means that theta 2 is equal to 5 pi over 6 plus pi over 8. Okay, same thing as before. 5 times 4 is 20 pi over 24 plus 3 pi over 24, and that is, I'm working with 23 pi over 24. Well done us. Well, that's great. And I need to compare that to the period that I'm working with, and this is why I've given us so much space to solve these problems. The period that I'm working with here is between the domain I'm working with is between 0 and 2 pi. But the period I'm working with, if I double check my k value over here, k is equal to 2. If k equals 2, then my period, call it capital P, my period is equal to 2 pi over k, and that is 2 pi over 2, and that is pi. So that means I've only considered one of my periods with these two solutions. I need to consider one more period. So if I'm considering one more period, my period is pi, then I'm working with, sorry folks, it's jumping all over the place, theta 3 is equal to theta 1 plus 1 period, and 1 period is pi. So that is I'm working with 7 pi over 24 plus pi. Well, what kind of a pi? We can go with 24 pi over 24. And that is I'm working with 31 pi over 24. Okay, let's check in on theta 4. Theta 4 is going to be equal to, right here, theta 2 plus a period. A period is pi, and that is theta 2. Oops. That is 23 pi over 24 plus 24 pi over 24. And we're working with right here 47 pi over 24. So all of our solutions all put together right here. Therefore, theta is equal to 7 pi over 24, or 23 pi over 24, or 31 pi over 24, or 47 pi over 24. Now, if you were able to follow this, great. If not, send me an email. But either way, you should be ready to handle the practice problems from section 7.5.